1946. Let me start by saying a few words about our lecture. Bill Thurston was born in 1946, graduated from New College of Sarasota, Florida in 1967, and obtained his PhD in mathematics from the University of California, Berkeley in 1972. He was a professor at Princeton for many years, before moving to Berkeley, where he is now director of MSRI, the Mathematical Sciences Research Institute, and also a professor at the University of California. He has been an active influence in the Geometry Center in Minneapolis, where he currently serves as a member of the Board of Governors. Dr. Thurston's primary interest is three-dimensional geometry and topology. He discovered a profound connection between three-dimensional non-Euclidean geometry and three-dimensional spaces, such as the space surrounding a knot. He also has interest in dynamical systems, the theory of groups and symmetries, as well as in the visualization of mathematics with the aid of computer graphics. Dr. Thurston is a winner of the Veblen Prize in Geometry, the Alan T. Waterman Award for the National Science Foundation, and the Fields Medal. He's a member of the American Academy of Arts and Sciences, the National Academy of Sciences. But what I just read to you, in fact, is something which is quite public information, because I picked it off the home page of MSRI on www. So this is what Bill Thurston, or at least MSRI thinks people should know about Bill Thurston. Now I'm about to reveal some less public information in the form of an anecdote. Several years ago, Lipton Bears was here speaking in Jerusalem, and he was talking on a subject which involved Thurston's work many years ago, the work related to Teichmüller space. And Lippe was, I think, a very gifted lecturer. And when he spoke, he usually placed the emphasis of his talk on the mathematics and not on the personalities of the people who created the mathematics. On this particular occasion, he said he was going to describe some of Thurston's work and describe Thurston as America's answer to Harry Thurstonberg. Now, I suspect if he were in Italy, he would have said America's answer to Bompieri, or Germany to Faltings, or what have you. But he was here in Israel. Anyway, I think that to all of us tells us who Bill Thurston is. And today I'd like to introduce him to you all. And he will speak on the topic of communication in mathematics. I remind you that this is the first of 3 lectures. The second and third lecture will be on Sunday evening at 7 o'clock and Monday afternoon at 4 o'clock. Not here, but in the mathematics department. Bill Thurston.
Well, what I want to talk about also will relate to my further talks on Sunday and Monday. I want to talk about some mathematics, but also about what is mathematics, and I think very closely related to that is how do we communicate or fail to communicate mathematics to each other. So I think there seems to be a lot of misconception about what mathematics really consists of, and what is the goal of mathematics. What do mathematicians do when they create mathematics, and what is it that we're achieving as we do mathematics? So to me, I've come more and more to the point of view that mathematics does not consist of a bunch of formulas, a bunch of definitions, a bunch of statements of theorems, but mathematics consists of ways that people think, They're ways of thinking about certain kinds of phenomena, ways of seeing patterns, ways of understanding patterns, and they depend very much. So mathematics depends very much on the human brain, not just. And of course, our brains are very, very intricate, very complicated, not that well understood. Everybody's brain is different. Everybody's, one thing we do know, though, about human thinking, about the human brain, is that also what we have very much in common with, not just with humans, but with many other kinds of animals, is that their brains our minds are made up of many different subsystems that are integrated only loosely at the top level. So for instance, we have certain very strong built-in linguistic facilities. We also have certain very sophisticated built-in visual processing facilities. Not just vision, though, but we have certain ways of understanding and dealing with space. And so when we think about a piece of mathematics, it makes a big difference, not just what the formal definitions are, but how it sits in our mind, how we think about it, how it is to us, and this is sometimes very hard to communicate because mathematics has the feel sometimes of a kind of imaginary world. We kind of internalize a lot of the we learn a lot of. As we learn mathematics, we internalize it, but it's very hard to think about the internal processes of thinking. So we think of it as an outside world. Okay, I'm not just going to talk this whole time. I want to focus on a certain example of some kinds of mathematics that I've encountered, that I've thought about, and we'll see a video pretty soon which shows a different way of, non-traditional way of trying to communicate some of this material. But I want to start a little bit by talking about it the way I think about it. So the mathematical subject matter. This is awkward. Okay. I'm going to stand up here. There's a little problem in geometry with this projector. Anyway, the mathematical subject I want to talk about is the theory of manifolds. So as a graduate student, I encountered this topic and various kinds of definitions, and I think my thinking went through a long set of different processes in how to think about it. Anyway, let's start with the picture. Let's start with some examples. So the example of here's the example of this is a picture of a sphere. A sphere is an example of a manifold. If you think of a sphere just as a picture I've drawn, it has one feel to it. But another way you can think of a sphere is actually as the surface of the Earth. And if you're a little, what I want to emphasize here is that there's a kind of insiders versus outsiders view of this surface. So if you're a person that lives somewhere on the surface of the Earth, then it seems like, well, of course, the surface of the Earth is bumpy. It may have mountains and so forth, but it seems like it's basically flat. And took people a long time to learn the difference between I mean, it took a long time for people to learn the notion that the Earth is round, because to any little person, any one person living on any portion of the Earth, the little region seems locally flat. There are certain, I think, built-in perceptions that we have that, for instance, there's a notion of up and down that seems to be almost built in. And it's hard to imagine that people live on the underside of the Earth and don't fall off. I mean, I certainly struggled over this notion for a very long time before I understood it. In fact, when I was first told that the Earth was round, I didn't picture it like this. I pictured it like a big hollow sphere, and that people are living on the inside of the Earth. And I wondered why I couldn't see Australia by looking up into the sky. I think that was when I was 5. I think it took me 2 or 3 more years before I understood that was outside, that this Earth was outside in. Anyway, the notion of a sphere that's huge, in a way, is different in the human mind than the notion of a sphere that's small. And when it's huge, it's easy to think of it as, I mean, it's much easier to think of it as basically flat, or having a prevailing trend of being flat, but on the whole, it's round. So this is the first example of a manifold. It's something that is locally like regionally like a flat plane, but globally it's different. Now the surface of the Earth could have been different from this. I mean, just from our local, just from roaming around on the surface, you could also imagine. Oh gosh, yeah, sorry. You can't see this. Is that better? It's not very good. I need broader ones, really. It might be better to do it on the blackboard, actually, than this. I think this overhead is too small. We have some chalk. Yeah, I'll do it on the blackboard. There's a different feel to the blackboard than to the overhead. Okay, another notion. The Earth could have been different. The Earth could have been round in a different sense. It could have been shaped like the surface here, a torus, or the surface of a bagel, and you can imagine little creatures that live. I want you to imagine little creatures that live on the surface of a torus. Make the creatures extremely small. And what would the surface seem like to them? So as a person, as this little creature, or think of it as a person. Think of it as a huge torus, and this is an explorer trying to understand the shape of the world. And as they walk around on the surface, so of course on the surface of the Earth, one way people say that they proved that it was round was by circumnavigating the globe, by having ships that sail around in a circle and come back to where they are. I mean, to me, this was never convincing because I could easily imagine sailing in a ship on a flat Earth and going around in a circle and coming back to where you are. I mean, to where you started. Just because you go in a circle and get back to where you start doesn't prove anything. Maybe you don't have a good navigational sense. Anyway, on the surface of a donut or a bagel, this is also true. You could go around in a circle and get back to where you are. You can go around in this circle and get back to where you are. And how do you distinguish these different kinds of potential shapes for the Earth? So we have to. One way to do it is you stand far away. Imagine you're looking at the Earth from the moon. Then it's immediately obvious. If you look at the Earth from the moon, you see that it's a round sphere. That's the. Or if the moon was or if the Earth was like this, you look at it from far away, you'll see it's a torus. You'll see it's shaped in this shape. But if you're on the inside of the Earth, if you live on the surface of the Earth, then what kind of experiment? How do you tell how it's connected to itself, how it's shaped? Okay, so now let's look at this picture. So there's a nice way to make a diagram of a surface that's shaped like a torus, and you can do it like this. You start with the torus. If you start with a torus and cut along a circle like so, you can imagine, for purposes of diagramming it, you unroll it and it becomes, if you imagine it made of a stretchy material, you can stretch it out and it becomes a cylinder. And now if you cut the cylinder on a curve like so, it goes like this, you can now unroll the cylinder and it becomes, and you get a rectangle. You can go back from a rectangle to a torus by gluing the top edge to the bottom edge and gluing the right edge to the left edge. This is one sort of diagrammatic picture. This is very closely related to something that, it's easy. One form of a torus in modern times is a computer screen or a video game screen, where sometimes there are games where if an object walks off, if you have a little monster or a person or whatever going off this edge, it suddenly reappears over here and keeps going. If it goes up to here, it keeps going, and so forth. Each point here is identified with this, and this person could walk in a straight line, and it would go in this pattern, like so. Maybe eventually they come back and arrive where they are. So this is one sort of physical realization. This is one model for a torus. Now, I want to go a little further. And now imagine, it is hard to really design careful experiments to show that you're on that you live on the surface of a torus instead of something else. But it's possible, but complicated. I don't want to get into it too far. But now imagine going one step further, and instead of imagine that the light. Imagine that a two-dimensional world where you have creatures that live in two dimensions, and where light travels along the surface of the torus. So it's so it's actually easier to imagine in this situation And actually, I want to immediately skip up to one dimension higher. So instead of taking this two-dimensional surface where we're only exploring along the surface, I want to go to one dimension higher and think of a three-dimensional space. Well, so imagine this. So instead of taking a square and identifying the opposite edges of the square together, I want you to imagine taking a cube, taking a three-dimensional cube, take a room, a rectangular room, and think of yourself as living in the room. And now imagine identifying the back wall to the front wall, the two side walls together, and the floor to the ceiling. So just as this two-dimensional surface can be constructed by taking a square and making those identifications, you can do the same thing in three dimensions. It takes a stretch of the imagination or a suspension of disbelief. You have to imagine that, this wall isn't really here. Change the shape of the room to be a rectangle. This wall isn't really here. If I walk over and I appear to go into the wall, really I'm over here, and I can continue walking. If I try to go through the blackboard, I'd suddenly emerge from the back of the room. Not only does your path of walking behave like that. I mean, if I go over that way, I suddenly appear over here. But you have to imagine that vision also works in the same way. So visually, if I look over in that direction, what do I see? Well, my line of sight continues going and comes back the other way. I'll see the back of my head. If I look up, what do I see? I see my feet. If I look down, we have to imagine this is a glass floor to make it a little bit more realistic so I don't fall. I look down, I see my head. I look over that way. I see the back of my head. Now, if I look at but there's a copy of me up above, there's a copy of me over that way, and of course there's a copy of me up above that person too. So if I look up one layer up, or diagonally, I see another image of myself. One layer above that, I see an image of myself. There'd be if you imagine yourself in this three-dimensional world made of taking a cube and identifying all its faces, really what you see is an infinitely repeated scene. Here I just have one person. Of course, there's a whole number of people. There's a lot of people, but everything is repeated infinitely often, to each side, up, down, back, forward. There's a vast army of people. They all repeat. They all do. Everybody does what their image does. If you start making it a little more physically realistic, there's a delay in the speed of light. I wouldn't necessarily have to talk very loud because whatever I say, you hear from all the voices from each side. Of course, there's a delay and an echo. You'll start hearing many, many echoes of every word. It might be hard to understand. Okay, so this is one example of a three-dimensional manifold. It's a three-dimensional space. In this picture where you take a cube and identify the faces and erase the walls, in any small region, if you imagine it's filled with fog, you couldn't tell the difference from just floating in the clouds up above. It's only when you look at the large-scale structure that you see this extra connectivity. This is called a three-dimensional torus, or it's often written T3. It's a three-dimensional torus. Now, there are many other ways to think about some object. As a mathematical object, this three-dimensional torus has many other descriptions. But to me, I think there's a lot of power in this sort of experiential description, in this description where you imagine yourself as living in this three-dimensional world. So I think, in fact, mathematics has a lot of power in going back and forth between what a person experiences and some abstract description. We have very powerful built-in processors for imagining things of this type. They're in fact quite flexible, so we can in fact change the rules in our minds and learn a lot in that way. But I mean, this kind of question of how something like this sits in your mind is what is often what has often been not effectively communicated between different generations of mathematicians. I believe that a lot of ways of thinking about mathematics have been repeatedly discovered by mathematicians. I mean, if you read carefully what they write, you can sort of sometimes understand how mathematicians were thinking, but as it's transmitted from one person to another, as it's written in papers, often ideas and ways of thinking about mathematics become formalized and codified, turned into algebra, turned into linguistics, turned into language, and they somehow often change their character. And I don't really know how to remedy that. It's quite hard to communicate ways of thinking. But with advances in technology, I think there are new avenues to explore. The video we'll see pretty soon is one example of that. What I'm doing partly is trying to soften you up for this video, which I think some people have seen. I hope not everybody. And okay. So yeah. Okay, so this is a three-dimensional torus. I want to talk a little bit about other possible worlds. Okay, I mentioned a little bit about a sphere, a little bit about the torus, but there are other surfaces. There are other two-dimensional worlds as well, other surfaces as well that are quite interesting, and then they have generalizations in space. So the next most complicated surface is the two-hole torus, like this. If you take a two-hole torus, you can you can also try to cut it up and flatten it out to better comprehend it. One way to do that is you cut along a curve like this, cut along a curve like this, cut along a curve like this, and cut along a curve like this. If you make all those cuts as indicated, I mean, it takes time to see what really happens. If you do this and carefully open it up, flatten it out, it turns out that you obtain an octagon and if you start with an octagon and then glue those two edges together, glue these two edges together, glue these two edges together, and glue these two edges together, it gives back a two-hole torus. And I mean, it would take a few minutes to carefully draw the picture. I don't want to take the time right now. You just have to take my word for it. Now, the strange thing about this is that on the surface, I mean, why it's a little hard to visualize, is on the surface, all 8 corners of the octagon come together to a single point. If you trace out what happens, gluing this edge to this edge, you can sort of bring them around, and this vertex gets glued to this vertex, and this one to this one, etc. But now you glue these two together, and this goes to this, and etc. Anyway, the vertices all, the corners of the octagon all get glued together to the same corner, and that's why it's a little hard to picture, but not impossible, not at all impossible. Okay. Anyway, it turns out that in order to make a good model of this, making it out of a octagon in the plane of the blackboard, for instance, is a bad idea. But there's a good picture in non-Euclidean geometry. But if you pass over to non-Euclidean geometry, then there's a good model for the octagon, which will geometrically work to give this surface. And non-Euclidean geometry is something which, well, there are many ways to think about it. There are many ways to think about it. One picture of non-Euclidean geometry, which is very standard, is just to take non-Euclidean geometry and model it in Euclidean geometry. So if you take the interior of a disk, and now I want to define a concept of a straight line in non-Euclidean geometry, and it's defined to be just a straight line is defined to be an arc of a circle that's perpendicular to this boundary of the disk. Anyway, then it turns out within this geometry, you can construct an octagon made of, its edges are made of 1, 2, 3, 4, 5, 6, 7, 8. These are 8 straight lines. You can find these so that the angles at the corners are all they're all 45-degree angles. When you do that, you can glue these sides together, and the corners, the angles at the corners all work out. So they'll lie flat in non-Euclidean geometry. Well, this is a kind of outside view of non-Euclidean geometry. I want to show this video called Not. Was made several years ago at the Geometry Center, and it gives a much, I think, a much better view of non-Euclidean geometry. It'll just take you into non-Euclidean geometry. You'll see it and experience it, and the video, let me just say, the video moves rather quickly. There's a narrator who has a very soothing voice, as if it should all be easy, but keep in mind the narrator probably didn't understand understand the mathematics very clearly. So this video really bears a lot of thought and attention, just like a mathematical paper might. It's all very closely connected, and it all makes a lot of logical sense. You can understand it on many different levels. In fact, the Grateful Dead have used it in their concerts before they became defunct. Yeah. Anyway, let's see this video and.
Welcome to the exhibit of Geometry and Knots. Knots are so much a part of our everyday world that we take them for granted. But mathematicians have found that studying even the simplest knots can lead into almost unimaginable spaces. In this movie, we'll take you on a short guided tour of the world of knots from a mathematician's perspective. Let's begin. This figure 8 knot can be untied since its ends are free. From a mathematician's point of view, this knot is no knot at all. But if we join the ends to form a loop, we can no longer undo the knot without cutting it. Now that's a knot. These 3 knots look different, are they? 2 knots that look different may be just different arrangements of the same knot. Sometimes a knot that looks knotted really isn't. Here are 3 intertwined loops. If you remove any one of them, the other 2 fall apart. Mathematicians call the union of several loops a link. By rearranging this link, we can see that the 3 loops are equivalent. Here is another symmetric form of the same link. In this form, it's called the Borromean rings. When we look at a knot, we don't usually think about the space around it. But to a mathematician, the space around a knot is just as real as the knot itself. Sometimes it's easier to understand something by looking at what it's not. The complement of a set is what's left when you take away the points of a set. So what's not a knot is called its complement. In 1988, Cameron Gordon and John Lukey proved that the complements of different knots can never be the same space. So studying the complements of knots helps us tell whether knots are the same or different. What is left when you take away the points of a knot or link from 3-dimensional space? What's left when you can't see the knot, not just because there's no matter there, but because space itself doesn't extend to where the knot used to be? We'll look first at a simpler picture. What is life like in a space with a single line missing? Or in a plane with a single point removed? We'll remove the point by pulling it upward, stretching the plane into a cone which grows sharper and sharper. Finally, the point disappears off to infinity, and the cone becomes a cylinder. The point at the cone's tip is special. It's called a cone point. As the cone steepens, The radius of a circle about the cone point increases, though its circumference stays constant. Meanwhile, an outsider looking from above sees the picture unchanged. We introduce an observer who lives inside the cone's surface and a few objects for him to observe. To the insider, light rays travel in straight lines. But the outsider sees those lines as curving around the cone point. To understand the insider's view, cut a cone made of paper and unroll it onto a plane. Since unrolling does not distort the paper, lines which are straight for the insider will be straight lines on the plane. This wedge is a building block for the cone and is called a fundamental domain. The two edges resulting from the cut represent a single line back on the cone. Anything crossing one edge reappears at the other. We can mend the cut by stretching, then gluing the edges. We get the outsider's view, where light rays look curved. The position of the imaginary cut is arbitrary. These insiders, touring the cone in their car, don't notice as we move the cut to follow them. They look right through the cut and see what seems to be another copy of the wedge. For special values of the cone angle, a whole number of wedges fit together neatly, but usually the remaining gap is filled with part of a wedge. Here's another way a cone surface differs from a plane. In a plane, only one straight line connects 2 points. But on a cone, there may be several. There may even be straight paths from a point to itself. We make our two-dimensional objects three-dimensional by stacking them up. The stack of cone points forms a line called a cone axis. The fundamental domain for this space is a solid wedge. Our inside observer sees many copies of the car at once. Which is the real one? They are all equally real. But the light rays from the car reach the observer from several different directions. Remember our question, what is life like in a space with a single line missing, or in a plane with a single point removed? As the cone angle decreases, the space we are looking at changes. Sometimes the wedge-shaped fundamental domains click together perfectly, like a jigsaw, and we get a symmetric picture. When n fundamental domains fit exactly around the cone axis, we say the axis has order n symmetry. As the order increases, the missing line recedes into the distance. In the limit, the missing line disappears off to infinity. The inside observer sees an endless straight row of cars, which are all a single car seen by light traveling different paths. Our building block or fundamental domain has become an infinite slab, and the cone is now a cylinder. We see how life would look in a space with a single line removed. Let's now turn to the question, what is life like in a space from which the Borromean rings have been removed? We place 6 cone axes with order 2 symmetry on the faces of a cube. This cube will be a fundamental domain for our experiment. Let's try and see what this space is from the outside. Remember that the walls of a fundamental domain determined by an axis of symmetry should be thought of as being glued together. We first glue the walls containing red axes, and then efface them as they are no longer necessary. Notice how the blue axes are joined together into an ellipse. We now glue the walls containing green axes. This joins the red axes into an ellipse. We have folded along 4 of the 6 faces of the original cube to form an ellipsoid. All that remains is to fold along the blue axis, which has also become an ellipse. To do this, we make the front and back hemisphere of the ellipsoid bulge up. The green axes too have joined to form a green ellipse. Notice what we have now, the Borromean rings. Now we've seen that the outside view of our fundamental domain is the Borromean rings. What is the insider's view like? Remember, around each cone axis, the insider sees 2 copies of every object. We first activate the red axes. The image from our fundamental domain gets replicated in the next door cube by the front axis. And both of these images get replicated by the back axis. And so on, until we have copies of the cube extending all the way to infinity in both directions. Next, turn on the green axes which face forward. This creates another infinite row of cubes. Turning on the other green axes reproduces these 2 rows to give 4 rows, and so on, until we have an infinite horizontal plane of cubes. Finally, when the blue axes are turned on, they make the 2-dimensional pattern be repeated in layers to fill up the whole space. This is what it looks like to live inside the space created by the order 2 axes on the sides of the cube. We can also work out what happens when the Borromean axes have higher order symmetry. For instance, if we want them to be order 4 axes, we must build a fundamental domain with 90-degree angles along these axes. We must modify our cube so it has right angles along its 6 axes. Impossible, you say? You may not have noticed it, but we're escorting you into Lobachevskian, or hyperbolic, geometry, where this and many other things are possible. This dodecahedron, in true hyperbolic perspective, has 90-degree angles between every pair of adjacent faces. When we look directly down on the red axis, we see that the faces meeting there make a right angle. We can glue 3 more copies of the dodecahedron around this axis. We can move our viewpoint inside this figure. Now we have 4-fold symmetry around one axis. Before exploring further, we'll remove the walls and change the shape and color of the beams. We can continue to add copies of the dodecahedron around each colored axis. First, let's do this for some of the available green, blue, and red axes. Eventually, the copies of the dodecahedron fill space without overlap. Just as we tiled ordinary space with cubes, we've tiled hyperbolic space with regular dodecahedra. Let's fly around a little in hyperbolic space to get a better feel for it. Notice how quickly apparent size changes as we move. This is one of the biggest qualitative differences between our everyday space and hyperbolic space. This is what it looks like to live inside the space created by order 4 axes along the edges of the dodecahedron. By adjusting the angles at the colored axes, we can derive similar pictures for order 5 symmetry, order 6 symmetry, and so on for all higher orders. Notice that as the order of the symmetry increases, the colored axes of the dodecahedron grow very short and move far away. Finally, in the limit, the red, green, and blue axes have receded to infinity. The resulting figure is called a rhombic dodecahedron. The 6 colored axes have been transformed into 6 vertices at infinity. To better understand the geometry of this shape, we add transparent walls to one copy of the figure and rotate hyperbolic space around its center. As the vertices at infinity pass behind our eye, we see interesting patterns. From inside the rhombic dodecahedron, the link has become infinitely far away, so that light can never reach it. This is the picture of the complement of the Borromean rings. We have succeeded in bending light so that it continues forever without hitting the link. This geometry is called a hyperbolic structure for the link complement. According to theorems of Mostow, Marden, and Prasad, there is at most one hyperbolic structure for any link complement. According to a theorem of Bill Thurston, all knots and links, with some simple exceptions, have complements that admit hyperbolic structures. Therefore, knots and links are completely determined by pictures such as this one. This concludes our guided tour. We've had a glimpse of how mathematicians understand knots and links and the spaces around them.
Some fairly classical treatments using axioms. Just talk about, Euclid's axioms for Euclidean geometry, and then you deny the axiom of parallels, and you start deriving consequences. It was all very abstract. And this is when I was an undergraduate, I had an intense feeling of, lack of reality of what it was. I think I started making paper models of the non-Euclidean plane, and eventually I got an internal sense of what non-Euclidean geometry is. But I think then the next time I encountered it, I think was in a complex variables course where it was described in terms of, there were formulas, fractional linear transformations, whatever. It had a very symbolic content. I didn't really quite believe they were the same thing. To me, the feeling of what it's like to live inside non-Euclidean geometry is the real picture of a certain mathematical phenomenon, and all the other things are derivative. It's of course hard to get it just from a short exposure, as in this video, but with computer technology, it becomes more and more real. So you saw a movie of flying through non-Euclidean geometry with certain things in it. On modern computers, you can actually, with your mouse, you control it, and you can really fly through it and play video games or do many different things, and you can learn to experience it just like Euclidean space. And I think all these attempts to communicate how people think to each other, I think they're weak. I mean, there's definitely weakness in the video. There's weakness in trying to explain it on the blackboard, weakness in just trying to explain it by words. I think it's, there are problems here that deserve a lot of thought and attention, and I think with modern tools, it's going to get, there are many possibilities that are opening up. I think what mathematics is really about is these ways of thinking, tools of thinking, and the only way that they're really going to be of use to society is if they can be sort of readily accessible. Well, enough of that. Let me ask, are there questions about anything, about the video in particular?
It seemed to me you were saying that the way to learn mathematics is to experience it, or the way to learn geometry is to experience it. I mean, that's...
No, I'm not saying there is a way to learn it. I think there's a lot of wasted effort sometimes in people struggling with mathematics. It's not purely, our ways of thinking are multimodal. They have many modes. I think often we end up concentrating on just a single mode. I think it's easy to ignore some of these modes, like, how it's easy to ignore these modes of, how it sits in our head, how we experience a certain kind of mathematics. But I think they're extremely important because I think you've become effective at thinking about mathematics in as much as you use your whole brain, your whole way of thinking. Not just a little piece of your brain, but your whole brain. So I don't want to have people just use vision. I think that's very weak, but somehow vision connected with symbolic uses.
You try to realize these ideas by other way of actually presenting three-dimensional Euclidean or non-Euclidean geometry, symbolic, spherical, in 2 or 3 dimensions. There are other experiments of the same sort that you show.
There are many experiments. Let me understand your question. You're talking about experiments at presenting it to groups of people. Yeah, in terms of courses, yes, there are many ways to do it. It actually takes a long time to fully, to communicate something, I think. So I think people learn a lot from, for instance, exercises. I've taught graduate courses where I give people paper and scissors and glue, and they construct models, and they definitely learn things that I think they haven't learned elsewhere, and it stimulates the imagination, and you can start asking many questions, and the trouble with video is that it's on the face passive. You're just sitting there watching. You need to have an active involvement, really, to learn, I think.
Just curiosity, if we were sitting rather than inside a complement of the Borromean ring, in the complement of some other knot,
Yes.
say with a non-Euclidean structure, would we actually be able to tell the difference? If you had shown us the video that...
Yes. If I had a good computer hookup here, so I could project it, I could draw a picture of a knot on my Macintosh PowerBook. I can draw a picture of a knot. It can compute the hyperbolic structure, and it can show you a picture, and you can immediately see the difference between different knots by the picture. So there are rigorous topological distinctions. Well, that's a good question. Of course, in a world, if you have an empty world, you don't see anything. Yeah. In this picture of the Borromean rings, it took these it took these rings, and then there were actually some columns made up of, it was like bars holding the wires apart, and that's what you actually saw in that picture. A more rigorous way to do it, if you want to distinguish knots and links, you can take some knot like, whatever it is, and you imagine drawing a surface to enclose the knot, a little torus around the knot. And one can do this in a precise geometric way, and then you look at that pattern. You can look at this pattern, and in the case of the Borromean rings, you would see some pattern that looks like this in a very square. There's a sort of very square pattern. And anyway, it's a distinctive pattern. In the case of another knot, you'd see another pattern. So this pattern, it looks like a pattern of spheres, but they're really toruses. And
is that the outsider's view or the insider's view?
That's the insider's view. The insider's view, yeah. And those are pictures that can be done in a few seconds on, well, it depends on the complexity of the knot, but in a few seconds on a Macintosh.
Where do I load this program?
You can ask me after. From the Geometry Center, you can find it. Other questions? I'd like to say something about these pictures that you saw of the insider's view of the complement of the Borromean rings. One of the effects, so the image on the screen was actually a wide-angle picture, and it would have been about correct if you were standing about this close. It probably seemed to be very, many people say that it makes them dizzy. It seems to be moving a little wildly around the edges. That's because it's a wide-angle shot. And if you're looking at it, well, most computer graphics is composed by people who are sitting at computer terminals that are about this far away. If you're at that distance, then it looks much more normal. And in fact, it starts seeming like a real universe that you could really live in. In fact, it's possible the universe is in that very pattern as far as anybody knows, but on a very large scale. Any other questions?
Yes. Can you say something about the interaction between the mathematicians and the animators or whoever has to work on this film like this?
It's an unusual group of people who did this. They were people who were, most of the people were both expert in, both had a lot of mathematical knowledge and a lot of computer and computer graphics knowledge. The one person who wasn't very mathematically trained was Del Maxwell, who had experience in it's called the flying logo business. When you see commercials on television where these letters come around flying into place and looks supposed to impress you. Anyway, there's also, of course, a lot of films from Hollywood are now, or wherever. A lot of feature-length films are also putting in a lot more of this computer graphics. So there's a whole industry, a large industry, doing this kind of stuff, and she had training in that. So there's a lot of expertise there in color and motion and timing and organizing a project that was important. But I think the hardest part was the mathematics and the mathematical modeling. And there were some very, very good people. For instance, the computer graphics of hyperbolic space, it turns out that the modeling the modeling of hyperbolic geometry is built in almost by accident into these modern graphics workstations, the silicon graphics workstation. So the sort of geometry pipeline they have is, I mean, just by changing little parameters, you can make it do hyperbolic geometry instead of Euclidean geometry. What's different, however, is lighting. So one thing that makes this look more real is that it has lighting. It has hyperbolic lighting and has rules for reflection of light and decay of light that are based on hyperbolic rather than Euclidean geometry. So, I mean, it takes a lot of different expertise, but I would say the people involved all could basically understand all parts of it. As time goes on, it's going to be a lot easier to do animations, just an individual person at an individual workstation doing it, because the hardware becomes a lot cheaper, the software becomes a lot better, and it will become a regular medium of communication.
There are no further questions. I'd like to thank the speaker and remind you once again that lecture, I think, more mathematical and will be held on Sunday on three-dimensional geometry and another one on Monday. Thank you very much.